The time to start thinking about heating and cooling is not when the truck rolls up with the ductwork in it. It's really long before that when you're starting to think about the framing. And here's a good example of a way that the NeighborWorks has been able to bring the ductwork, in fact the entire heating system, inside the conditioned envelope. Traditionally the heating system is installed kind of as an afterthought, and it's run through attics and crawl spaces, which is really outside of the building. So here we have an example of a little bit of forethought that was put into this project, and they've created a space that will be insulated, and technically it's inside the thermal boundary or inside the conditioned envelope. It's a good time to introduce Greg Davenport from Mitsubishi, because he's helped NeighborWorks kind of optimize their heating and cooling system. Welcome, Greg.
Hi. So I'm going to add to what Bruce just said here, which is there's a lot of intentionality in the HVAC design here that comes even before they start putting up the framing. They use their rater to also provide HVAC design services here, which includes a manual J load calculation, manual S, equipment selection, and then they come through and do a really nice duct design so that we can use right-sized equipment, get good energy efficiency and good comfort. And what we're finding is we can use smaller systems that cost less, and they get better energy performance and better energy comfort out of it. An example of that would be where we're going to put the horizontal ducted up here in this truss tunnel, and they've actually done a great job team working with their truss manufacturer to design this little box up here that allows them to put a horizontal ducted system in, and we'll have small branch ducts that go off to each of the bedrooms upstairs. So you have a small horizontal ducted heat pump system that serves all the upstairs bedrooms.
Thanks, Greg. And having you guys at the table, I think, has been pretty critical to think through what the systems can handle. I think for an eye-opener for us is, the efficiency of our space is so critical, and taking up space in a corner for another vertical or down below furnace was something we did. We put them in those locations. But the opportunity here is to create that space can be used by other things. In this case, it's our laundry room. Now we're putting it up above some space that just really isn't used inherently. Now this design has changed. I think it was bigger when we first started. We tried to accompany and do lots of things. We've kind of minimized it. They've gotten deeper based on the equipment detail and the need for service. So we paid attention to not just how do we get it installed, but how do we service it as it relates to if there's anything that ever needs to be done. They can easily be dropped if need be, and it's all within this conditioned space, and we're not having to crawl in up to other areas that are outside of the conditioned space. Attics can get up to 160 degrees at times, and so now you're trying to cool your house with your ducts in a space that's working against your equipment, certainly working against your efficiencies.
The important part is to deliver comfort to every room of the house. And each house is a little bit different, and so it takes a bit of thought to plan that system effectively. And that's where your energy model and your manual J heating and cooling calculations are going to come into play. So it's really important to kind of engage your energy rater and your HVAC contractor during the design phase so that you can anticipate these things and select the system that's going to work best and most efficiently in your home.
So many builders do ducts outside of conditioned space. It's easy, but it's not very good in terms of energy efficiency and comfort. I've been working with NeighborWorks for about 3 years now, and early on we decided we would do all the ductwork inside a conditioned space, which allows for smaller systems and that cost less. But one of the things we're seeing in codes around the country is they're moving builders more and more towards ducts in conditioned space or deeply buried ductwork. I will predict that in 5 to 10 years, many states will have codes that require ducts inside conditioned space. And what we're seeing nationally with better codes and more high-performance builders is heating and cooling loads on homes keep coming down lower and lower. So doing systems like this becomes easier and easier with smaller heating and cooling loads. The other thing is when you're using right-sized equipment, which the variable capacity heat pumps are really good at because they come in so many different size options, heating and cooling systems for modern homes have much less heating and cooling need. The measure is BTU, when they do HVAC design. A traditional home built 20 or 30 years ago would have 40, 50, 60,000 BTUs of heating load and something close to that in terms of cooling loads. These houses that NeighborWorks is building here, their heating loads are on the order of 18 to 30,000 BTUs, depending on the size of the house.
Interesting idea to have the truss manufacturer create the basic framing for the tunnel. The truss tunnel is a great term. And you've kind of done some pickup framing within that. So, Bud, will you explain kind of how you ordered this and how it was delivered and what you had to do afterwards to finish it off?
Yeah, so, a series of trusses kind of bring your roof together. In this instance, we did think through, we know we wanted this tunnel for our HVAC system. The reality is we only needed to change three trusses to accommodate that. By them changing 3 trusses and allowing for that tunnel to take place, our framers really did an on-site framing, if you would, to fill in areas that you still need to insulate around the outside perimeters, and you need to hang some sheetrock. And so you need that space to hang the sheetrock and to provide for that tunnel to be well insulated.
So the framers lined it with OSB to create kind of an air barrier at the top, and then they put in the rafters, the false rafters there to support the drywall below.
Yep, and all of that will be insulated inside with seal foam, and then be insulated on the outside, certainly with our R50 in the attic.
Mm-hmm. So pump R50 of insulation over this entire attic, and you can see on the far side there's plenty of vertical space because of the way your roof is framed to get the full R50 right up over the outside of the plate. And on the other side there's the raised heel that gets you at least R21, which is a pretty good compromise.
Yeah.
It's a great idea. What's really nice about attic insulation is that it protects you from heat loss in the winter, but it protects you from heat gain in the summer.
Yeah, sure
and
does.
In combination with the ventilation, you can make sure that you've got a nice cool roof pretty much all year long.
Yeah.
But can you speak to the cost and the difficulty with your truss manufacturer of having them make this adjustment?
Yeah, the cost is very minimal, under $300 to have those adjustments made, and I want to say it's even less than that. In reality, by the time we add in, you already have OSB on site, you already have 2x4s on site, so that's not a big deal. Making those 3 adjustments was an easy fix. And in some cases, where you would normally put a dormer, so you would move 2 trusses together, I think there's an opportunity as NeighborWorks needs to get a little more height out of it. We've looked at just creating a dormer space, if you would, and then framing in that shelter for the HVAC system. So it'll allow you to actually get up and you're actually standing somewhat inside of a room, but still gives you that energy layer around the roof line.
So in contrast to this truss tunnel system that NeighborWorks is using here, some builders will do a drop-down soffit ceiling approach in order to accommodate a horizontal ducting. I want to talk for a minute about the 2 Mitsubishi systems we have here, but before I do that, I'd like to introduce Jordan from Quality Heating. He's been a great team player here with NeighborWorks, with Building Energy HVAC design, and with Mitsubishi doing all the installations here. So on the outside of this house, we talked about it a little on the inside, we have 2 small, what's called one-to-one systems, as opposed to a multi-zone system that can handle 2 or more inside units. And what's interesting, I talked earlier about how the heating and cooling loads on these houses are very small because they're building energy efficient homes. Well, it turns out that that is a 12,000 BTU system here, and this is a 9,000 BTU system here. So the whole heating load for this house on the coldest day of the year is about 21,000 BTU. And what's great about these 2 small independent systems is if you need just a little heat downstairs or upstairs or wherever, each system can give you just a little bit. One of the issues we're running into in the new high performance homes as the heating and cooling loads keep coming down is that on the coldest day of the year you might need 21,000 BTU, which is what this system is capable. But on all the what we call shoulder season or in spring when you need just a little heating or cooling, if you don't have good variable capacity systems, these systems will short cycle and go on and off. It's not good for the equipment. It's not good for your energy use. It's also not good for your comfort. So this is a smarter design to use smaller independent systems here for comfort and energy. What's also interesting is the cost by doing 2 small independent systems is about the same as doing a larger multi-zone system. Jordan, do you want to talk about the installation design and working with the builder and the HVAC designer a little bit?
Absolutely. So having the 2 independent, just to elaborate a little bit on what he was saying, the upstairs unit might call for cooling, whereas the downstairs unit doesn't need cooling. Having 2 separated systems, they can do that.
NeighborWorks is on the leading edge with their low-load homes, energy-efficient homes, but other builders around the country are just a few years behind them. We're seeing this all over the country right now. So these kind of leading-edge best practices that we're seeing here with NeighborWorks are things that other builders, other HVAC contractors need to figure out soon. Jordan, you do a really nice job installing these up off the ground above the highest level the snow could come at. Do you want to talk for a minute about the importance of getting this higher than the snow and why we do that?
Yeah, so in our area, I believe it's 6 inches that they want us to maintain off the ground for our snow load typically. 4 or 5 years ago, we had about a foot to 16 inches of snow constantly. So our idea is to keep this off the ground. I think we're at about 2 feet here. Just based on the fact that these do drain, you want to keep ice away from the units, you want to keep snow away from the units, all of that can damage it.
So one other note on these variable capacity heat pumps here, these are cold climate systems. They're designed to operate in areas below about 32 degrees and be energy efficient. That is one of the new areas in variable capacity heat pumps, and there's a lot of need for training out there in the marketplace about how to design and install cold climate heat pump systems well. And you can see both this logo indicates they're cold climate capable systems. And when you do that, you have to make a few small differences. One of them is make sure you put the outdoor units above the snow level. It is surprising how many parts of the country we see where installers don't get them higher than the snow, and that can damage or destroy the equipment pretty easily.
We're upstairs looking at one of these PEAD units, the ducted units that we designed, and I've got Heath here with Building Energy that helped us design it.
I'm Heath, and I did the HVAC design for this home. It's a PEAD, horizontal ducted unit heat pump that Jordan and his team installed. It's got what we call a pair of pants coming off of the front of it to run down the truss tunnel on each side and supply every room with air. It's a great system. It's totally concealed. It's extremely quiet. Did great on all of our testing. It's going to be a great unit for this home. It's also got a fresh air system directly from outside on a motorized damper. So the motorized damper fresh air intake system allows the ventilation to be controlled so we don't over or under ventilate. It also allows it to be dispersed into the HVAC system that disperses it throughout the entire home. This improves indoor air quality, makes sure that our ventilation is high quality ventilated air for the homeowner's comfort. So for our energy testing, we do a duct test and a balance. Both tests went extremely well for this unit. The ducts are all in conditioned space, and by our standard, we don't actually have to do a test on those. We do it anyway so that the builder knows. These scored in the low teens, which is extremely low. It's all metal hard pipe and it's mastic very well. And what that does is it allows the unit that you're paying for, these units are very high efficient. And so when you pay for a unit that's high efficient, if you don't have a good system attached to it, you lose that efficiency. That efficiency goes into the unconditioned areas, and that's all money that you are spending to be comfortable in your home and pushing it to a place where you're not going to gain any benefit from it. So Jordan and his team did a great job on the install here. The test went flawlessly, and really it's just a great system overall. I forgot the rest of it.
Yeah. I mean, one thing to add to that would be in your traditional homes with leaky ductwork, you had your standard high-fired large pieces of equipment. It would satisfy the home, but you're wasting tons of energy, like Heath just talked about. When we started going to high-efficiency equipment, what the whole industry abroad saw was it exacerbated all those problems because it can now vary it down to try to add comfort to the house, but what it was doing is it was just exacerbating the leaks throughout the house. So when we seal things like this, the system size can drop down. You get the airflow where you want it in the house, not to areas that nobody's at, in attics and crawls.
With forced air heating systems, you're blowing a lot of air into rooms, and then sometimes people close the door, right? And then what does that do? That traps all the air behind that door. How can we solve that problem?
So in this situation, we have, like you just discussed, our centralized return air in the hallway. And what we have above it is what we call transfer grills. So as that door shuts, it still allows a return air pathway back to the unit. Some of the other homes that we're doing, they also have door undercuts, which is something that we'll do just to make sure that you don't get that pressure buildup in the room.
What about a jump duct?
You can do jump ducts too. And a jump duct you would see it in the ceiling like you do here, and we would jump it back to the main return air.
Jordan and Heath, can you explain a little bit about how you guys have worked together to do the heating sizing calculations and some of the design aspect of this project?
Absolutely. So when Greg approached me on this, he had talked about working with Heath and making sure that we had a good, clear communication between all of us. And I know typically for an HVAC guy, that's not the case. And with Heath, it's been great. We work really well together. Greg's got good designs that have worked in other areas that we've just fit into this mold.
Yeah, it's really easy to design these things, but having the design actually fit the construction and the install is where we run into problems, right? I can draw anything. I can draw anything in the world, but it's got to work for him. So working with him to say, all right, this is what we can do, this is what we can't do.
Heath, you're already doing an energy model, which requires you to do building takeoffs. How much extra work is it to take those takeoffs and apply them in a manual J calculation?
Not much. I mean, we are getting most of that information from the builder already. It actually makes our energy model more accurate because I know what they're going to do from the start, and then I can go out and verify that in the field as they are doing it, they aren't doing it, or whatever correction needs made. And then at the final verification, I don't have to worry as much, did they change something while I wasn't looking, because I designed the whole thing from start to finish and I verified it on the way through.
It's really remarkable that you guys have found this way to collaborate together. Thanks a lot.
Yeah, absolutely.